Moving an LLM from prototype to production makes the runtime choice critical. It affects control, cost, latency, security, and the operational work your team takes on. We'll use these deployment models as a practical map for choosing the right foundation. We're now moving from GenAI architecture design into production deployment. You already know the core building blocks: applications, APIs, orchestration, retrieval, vector databases, and model endpoints. Next, we'll evaluate where those pieces can run. Then connect those choices to CI/CD, infrastructure as code, versioning, and release readiness. Deployment is a set of trade-offs, not a single architecture decision. A chat assistant, RAG system, batch summarizer, embedding workflow, and agentic application all place different demands on latency, throughput, data control, and operational complexity. The question is not always, where do we host the model? Often, the model stays behind an API, while the application, retrieval layer, guardrails, and orchestration are what you deploy. In enterprise environments, the best answer is often hybrid. Different deployment patterns for different workloads, with governance, reliability, and cost kept predictable. A managed LLM service lets your application own the user experience, business logic, security controls, and orchestration layer, while the provider runs the model. When language intelligence is needed, your backend calls the hosted service through secure HTTPS APIs and returns the response to the user. This avoids running GPU clusters, managing model serving, or handling frequent model upgrades yourself. The trade-off is dependency. You still need to plan for rate limits, cost monitoring, data residency, secrets management, logging, and behavior changes when models are updated. For many teams, this is the fastest path to production. In production, client apps should not call hosted models directly. Put an enterprise GenAI gateway or backend between applications and providers, so identity, authorization, routing, logging, and policy checks are enforced consistently. This control layer can apply rate limits, tenant isolation, approved prompt templates, model allow lists, and data loss prevention before anything reaches a provider. It also captures latency, token usage, errors, safety outcomes, and feedback. Just as important, it hides provider-specific APIs, so teams can switch models, fail over, optimize cost, or use multiple providers without rewriting every application. Managed AI platforms occupy the middle ground between hosted model APIs and fully self-managed infrastructure. With a simple API, the provider owns most of the runtime. With self-hosting, your team owns the stack end-to-end. Platforms like Vertex AI, Azure AI Foundry, SageMaker, Databricks Mosaic AI, and Snowflake Cortex share that responsibility. They provide model hosting, registries, endpoints, auto-scaling, monitoring, IAM integration, and experiment tracking. The benefit is cloud-native governance with less platform engineering. The trade-off is vendor-specific workflows, dependency, less customization, and pricing that may be harder to predict. Kubernetes often becomes the control plane for an LLM application, even when the model itself runs elsewhere. Each capability is packaged as a container: the API, prompt orchestration, retrieval service, document processor, evaluator, and background workers. Kubernetes supplies the operational foundation: deployments for rollout, services and ingress for traffic, secrets and config maps for configuration, and persistent volumes for state. The cluster then connects outward to vector databases, storage, identity, observability, and hosted LLM APIs. This gives teams repeatable releases, workload isolation, and a portable base for platform engineering. For GenAI workloads on Kubernetes, the goal is to turn a working container into a reliable production service. Start with auto-scaling. API pods and workers should grow or shrink based on real demand, not fixed guesses. Keep configuration outside the image with config maps, and protect credentials with secrets or an external secret manager. Isolation matters too. Use namespaces, quotas, network policies, service accounts, and RBAC AC to limit blast radius. For GPU workloads, dedicate GPU node pools, install device plugins, and use taints, tolerations, and scheduling rules so expensive accelerators are reserved for the right jobs. Self-hosting is like running your own power plant instead of buying electricity from the grid. You gain control over where data goes, which models run, how latency is tuned, and whether systems can operate offline. That can matter for fine-tuned models, internal assistance, domain RAG, embeddings, re-ranking, and batch inference. But control comes with ownership. Your team now manages GPUs, model loading, scaling, patches, reliability, monitoring, and cost utilization. Self-hosting pays off when platform engineering and automation are strong enough to make that responsibility repeatable. Once you self-host inference, the serving stack becomes a major design choice. VLLM is often the default for high-throughput LLM serving because continuous batching and KV cache management help keep GPUs busy. Hugging Face text generation inference is a strong fit when you want optimized transformer serving with a familiar model workflow. Kserve, RayServe, Triton, and Seldon broaden the focus to scalable, Kubernetes-friendly, multi-model operations. The right answer depends less on popularity and more on your model architecture, latency target, utilization goals, and how well the stack fits your platform. GPU inference is a pipeline, not just a large machine. Requests enter through a gateway, wait in a queue, and are routed to model servers on GPU node pools. Those servers load model artifacts from storage, then generate tokens under tight memory limits. The main tuning levers are batch size, context length, quantization, tensor parallelism, KV cache strategy, and whether responses stream token by token. The goal is high GPU utilization without breaking P95 latency. Watch tokens per second, queue depth, memory, and idle GPU time, because that is where cost leaks tend to appear. Serverless is a good fit when GenAI tasks are short, event-driven, and intermittent. Examples include prompt routing, lightweight API orchestration, webhook handling, embedding calls, or background document processing, such as summarization and metadata extraction. The payoff is speed. Deploy quickly, scale automatically, and avoid paying for idle capacity. But serverless is not a universal inference platform. Cold starts, time limits, memory ceilings, network latency, and observability gaps can hurt reliability. Be careful with long-running jobs, large models, GPU-heavy serving, or strict P99 latency requirements. For those, dedicated containers or managed endpoints usually fit better. Production. GenAI often involves more than a chat endpoint. Documents may arrive through uploads, storage events, or scheduled jobs, then move through a queue so ingestion is decoupled from the user experience. Workers parse files, split content into chunks, generate embeddings, extract metadata, and update the vector index and data stores. The queue acts as a shock absorber. It smooths spikes, supports retries, and prevents failures from blocking users. Build these pipelines to be idempotent, observable, and replayable, with backpressure controls and dead letter queues for records that need repair. In practice, enterprise GenAI rarely fits a single deployment model. A typical RAG assistant might run APIs and orchestration in Kubernetes, call a managed frontier model for generation, and use serverless jobs for document ingestion, indexing, and scheduled refreshes. Some teams self-host embeddings, re-rankers, or specialized models when privacy, latency, customization, or high-volume economics justify the operational burden. The key is to make each choice explicit. Capture the decision in an architecture record, validate cost and risk assumptions, and confirm the team can operate the component before committing. The big takeaway is that deployment is not one-size-fits-all. Hosted APIs, managed platforms, Kubernetes, serverless patterns, and self-hosted GPUs each trade speed, control, security, latency, reliability, and cost differently. Most enterprises will combine them. Next, we'll make those choices repeatable with CI/CD, infrastructure as code, versioning, release strategies, and operational readiness.